In this module, we will define what a sequence is and give several examples. Definition. A sequence is a function f from natural numbers to r. That's it. Probably the shortest definition you have seen. Even the definition of empty set was slightly bigger, I believe. So, we will be studying sequences. This notation, this functional notation is not always convenient. So, usually the simplest way to describe a sequence is to just list out the elements as x1, x2, x3, ... or a1, a2, a3, ... This is sort of like a dynamic notation for sequences. Often we will just list 3 or 4 terms and it should be apparent what the rest of the terms are. You should be able to guess what the rest of the terms are. Okay. So this xi is just supposed to be f of I. So essentially sequence are just lists. Please connect back this to the definitions of countability. More precise notation for sequences is something like this. You just put xn in the parenthesis, or if you want to be ultra precise, you can use something like an n equals 1 to infinity. Okay. The last notation has the advantage that I can always change it and say an n equals some k naught to infinity. Okay. So we can always start a sequence not from just x1 but from some further point along, sometimes even negative. You can start from x minus 3, x minus 2, so on. These are minor modifications to the definition of a sequence, so we will not be ultra precise in defining them. However, we might occasionally use such sequences which do not begin at x1. Okay. So we will in the future we will just use any one of these notations for our sequences. Now, sequences are very important in analysis because many of the major concepts of analysis, including limits, continuity, differentiation, integration, and even sum of infinite series, can all be phrased in terms of sequences. So, our objective is to study what it means for a sequence to converge to a particular number or approach a particular number or limit of a sequence to be a particular number. Before we get to that, it's always good to see lots of examples. Usually I recommend we see 7 examples at least, simply because 7 is the smallest number that a random person on the street may not be able to identify whether it's prime or not. Please don't test it in the real world. This is just my personal experience. Let's just see some examples of sequences. Example 1. Consider the sequence 1, 2, 3, ... So if you want to be ultra precise, this is the sequence defined by f of n equal to n or n running from 1 to infinity, or I'm going to be done here. I'm not going to belabor this anymore. So this is a sequence of real numbers that is ever increasing. Clearly, it does not tend to a point on the real line. But in an intuitive sense, this sequence seems to converge to the point infinity, though infinity is not a point on the real line. We will see more about such sequences. These are sequences that diverge to infinity. We will study these sequences also. But that's not the central point of the course. So let me give another example which is more relevant. Consider the sequence 1, half, 1 by 3, 1 by 4 and so on. This is just the sequence xn equal to 1 by n. Okay. Sometimes we shall be even more loose and just say the sequence 1 by n. Sometimes we will just say the sequence 1 by n. Okay. Now this sequence is ever decreasing. Not only is it ever decreasing, it seems to be approaching or limiting to the point 0, the number 0. We will make precise what this means soon. Let's just twist this example a little bit. Let's consider 1 minus 1 by n, the sequence 1 minus 1 by n. The terms look like 0, half, 2 by 3, 3 by 4, and so on. Okay? This is a sequence that is ever increasing and seems to converge to the point 1. Okay? Now let's twist example 2 again and consider this sequence, example 4, which is the sequence minus 1 power n by n. How does this sequence look? Well, the first term is minus 1, then it's plus half, then it's minus 1 by 3, then it's plus 1 by 4, and so on. If you observe carefully, this sequence is neither increasing nor decreasing. It seems to be jumping here and there. But if you just collect together all the terms coming from the odd xn's, where n is odd, you get the sequence minus 1, minus 1 by 3, minus 1 by 5, and so on. Whereas if you collect all the even terms of the sequence, you get half, 1 by 4, 1 by 6, and so on. Now, a moment's thought will tell you that both these in quote subsequences seem to be approaching 0, and so does the main sequence minus 1 power n by n. That also seems to be converging to 0, even though it's jumping around. One common mistake that students make in a first course in real analysis is to think that if a sequence is convergent, it cannot jump around like this. It must either be increasing or decreasing, at least after a point. That's not true. So this example motivates another definition. Let xn be a sequence. Let sigma from natural numbers to itself be an increasing function. What does this mean? This means that sigma of n plus 1 is greater than sigma of n for all n and n. Okay? Then the sequence defined by f from n to r, n mapping to x sigma n is called a subsequence. Is called a subsequence of xn. So if you think about this definition, all it's saying is that a subsequence is nothing but terms selected from a sequence but in order. You can ignore some terms, but you will have to go in the same order. You cannot change the order of the terms appearing in a subsequence. So another way to think of a subsequence is like this. You are given numbers n1 less than n2 less than n3 less than dot dot dot, and you're just considering the new sequence x and k, where now k runs from 1 to infinity. The sequence is no longer indexed by n, but it's indexed by this nk, and k is running from 1 to infinity. Okay? Now, let's see some examples, some more. Continue with the examples of sequences, at the same time see examples of subsequences also. Example 5. What you do is you define xn in a somewhat convoluted manner. It's 0 if n is odd, 1 if n is even. or rather let me interchange. There is no particular reason why I'm going to interchange, but it will be more useful. 0 if n is even, 1 if n is odd. Okay, so the sequence goes like this: 1 0 1 0 1 0 dot dot dot, keeps going. Again, it has two interesting subsequences: 1 1 1 1 0 0 0 0. Note, these are not the only subsequences. These are not the only subsequences. Any sequence that has only ones and zeros is a subsequence of this particular xn. Please check why that is true. But these two, 1 1 1 1 1 and 0 0 0 0 0, are interesting subsequences. These are known as constant subsequences. A sequence that is just a repetition of a single constant is called a constant sequence. Not a very creative name, but at the same time, no need to be creative when it's not needed. Okay, now let's see some complicated examples. Example: I believe we are at example 6. We are almost there to our goal of 7 examples. Xn is 1 if n is divisible by 10, 1 minus 1 by n otherwise. Okay. This sequence also has some interesting subsequences. One of them is 1 1 1 1 1. Okay. Another interesting subsequence is 1 half dot 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 1 by 9 and no 1 by 10, because it's 1 if n is divisible by 10, then 1 by 11, so on. Okay. Now this sequence looks to be convergent because the terms seem to be decreasing, but every once in a while there is a pesky 1 that shows up and ruins the day. So this sequence will actually not be convergent. The final example, example 7, is a very famous sequence. It's the Fibonacci sequence. How is this defined? Well, you define A1 to be 1, A2 to be 1, A3 to be 2, A4 to be 3, and so on. How does this go? Well, an equals an minus 1 plus an minus 2, and n has got to be greater than 2 for this definition to make sense, and we define a1 to be 1 and a2 to be 1. Okay, so it's the sequence that goes 1 1 2 3 5, so on. Clearly this sequence also seems to diverge to infinity, but we can form some interesting sequences from this Fibonacci sequence by considering reciprocals. We can consider the reciprocals. Reciprocals will be 1 1 half 1 by 3 and so on. Okay, and you can see that the reciprocals will sort of converge to 0. Okay, so this concludes the set of examples. From the next module we will define convergence and we will solve many examples, find the limits then find the sums of series, show that a particular sequence is not convergent, show that a particular sequence diverges to infinity, so on and so forth. We will solve plenty of problems. This is a course on real analysis, and you just watched the module on the definition of sequence and examples.